Welcome back to Chapter 14, Part 4. We're still in the introduction of inference. Remember, in this particular chapter, we have three simple conditions that are assumed. That we have our samples are simple random samples. The variable we measure has an exactly normal distribution in the population, and we know the population standard deviation. Now we're going to finish up with confidence interval by looking how we can do this in Minitab. So here's a problem. We say an urban economist wishes to estimate the mean amount of time people spend traveling to work. So he obtains a simple random sample of 50 individuals who are in the labor force and finds the mean travel time of those 50 individuals to be 24.2. Assuming the population standard deviation of travel time is known and it's 18.5 minutes, construct and interpret the 95% confidence interval for the mean travel time to work. Now again, we're assuming that these travel times are normally distributed, and they give us the standard deviation, the population standard deviation of 18.5. We're going to use the mean of the sample of 50 to produce a 95% confidence interval. So we would put, here's our Minitab commands. You would type 1Z, and you would type N and your X bar. So remember, our N was 50, because that's the sample size, and X bar was the mean of that sample, which was 24.2. We put a semicolon to say, hey, Minitab, wait a minute, I need to give you some more information before you calculate anything. And you give it and you tell it what its sigma is, the population standard deviation, and that's 18.5. Now we do our last semicolon, because now we have to tell Minitab what confidence level to do. And in this case, we're doing a 95% confidence interval. Once you do that, you do a period. When you hit enter, you will see the resulting in the sessions window. And right there you see our confidence interval in blue. So how would we interpret this? We would then say we estimate that the mean amount of time people spend traveling to work is between 19.1 and 29.3 minutes with a 95% confidence interval. So here's the general code that you would use in Minitab to do a confidence interval with the given assumptions of this chapter. Now this is if we're given X bar and N. We can now look if we're given data, sample data, and how we can use Minitab. So whatever column our data is in, so in that first line we would say we're doing a 1Z, take the data from column C, whatever, where Y is whatever column our data is in, give the sigma that will be given in the problem, and tell what confidence level we want to do. And here's a nice way that, especially when you do your Minitab, how you would write up the possible interpretations of your confidence interval. So we're going to go back into a very important part called the margin of error. This margin of error is what gives our confidence interval its length. We're going to add a certain number to the sample mean and subtract that certain value, that margin of error, from the mean. So all the margin of error is what we see after the plus or minus. So it's our critical value times the standard error. And what we find out is the larger the sample size, the smaller our margin of error. The smaller the level of confidence, remember, our critical value will decrease. That will also reduce the margin of error, which will obviously reduce the width of the interval. And so these are ways that we can reduce the margin of error. We have, when we did our Minitab, that the margin of error for our 95% confidence interval for this problem is 5.13. If we do a 99% confidence interval, our margin of error is 6.7. So if we increase our confidence level, we're going to increase the margin of error. It's clearly seen. And we did that in all the different examples that we did in the last series in Part 2. Now it's time to begin hypothesis testing, tests of significance. We need to determine the null and alternative hypothesis for a claim. And then we need to understand what we mean by the null and alternative hypothesis. Once we do that, then we state conclusions to the particular hypothesis test that we do. Now, hypothesis testing is part of inferential statistics. Hypothesis testing and estimation are two different approaches to two similar problems. Estimation is the process of using sample data to estimate the value of a population parameter. That's our confidence intervals that we've just been doing. And hypothesis testing is the process of using sample data to test a claim about the value of a population parameter. That's what we call tests of significance. Now, when we're doing a hypothesis test, we want to determine whether a particular claim is believable or not. This is one of the most common goals of statistics. Now, the process is called hypothesis testing. So a claim is made, we get evidence, we collect our evidence, then we analyze our evidence, our data, and then we make conclusions about the claim based on the data that we collected. So looking at hypothesis testing, it involves learning how to state our claim in terms of values of a population parameter, and then how to quantify how confident we are in that claim. That requires statistics. So let's look at a problem. A car manufacturer advertises that a certain model of his car achieves 29 miles per gallon on average. However, a competitor believes that the manufacturer was overstating what his car could achieve as far as miles per gallon. So we need to test some number of cars. For each of these cars, we're going to record how many miles per gallon it gets. Now let's say that we had a sample of 100, and we calculate that sample mean it was 27. What we have to do now is we have to say, is that 27 miles per gallon consistent with the manufacturer's claim or not? So then we'd have to say how confident we are that the manufacturer has significantly overstated the average achievable miles per gallon. Now, we'd like to be able to make statements such as, we're pretty sure that the average miles per gallon is less than 29, or, hey, it's believable that the average miles per gallon is equal to 29 miles per gallon. A hypothesis test for an unknown parameter is a procedure that's based on sample evidence again. And, of course, we have to use probability. So we're going to use it to test a specific claim about a particular value of the parameter, or a value of the parameter. Now, we can have many unknown population parameters. The one we focus on in this chapter is the mean, mu. But we could also do hypothesis testing about population proportion or standard deviation. Now, since a claim can either be true or false, hypothesis testing is based on two types of hypotheses: a null hypothesis and an alternative hypothesis. The null hypothesis is a statement regarding the value of a parameter to be tested. It's written as h sub 0, which we read as h naught or h sub 0. It's always a statement of equality. It's a statement of the status quo, or no difference. It's assumed to be plausible until we have evidence to the contrary. So we're always going to believe the hypothesis test unless we have evidence to the contrary. And when we talk about evidence to the contrary, we'll be using our probability to give a quantitative answer to that. So let's look at an example. That car manufacturer that advertised that a certain model of the car achieves 29 miles per gallon on average. The null hypothesis there is that, that the mean miles per gallon of his car is 29. That would be our null hypothesis, the status quo, what is believed to be true. So now let's look at the alternative hypothesis. Now that's the claim that we have to test. We have to have proof for this and test this particular claim. So it's written as h sub a for the alternative hypothesis, and it's read HA or h sub a. It never contains a statement of equality. It represents the claim that we seek evidence for. Now, again, there are different types of alternative hypothesis, and it really does depend on what your problem is. So in this particular car manufacturer problem, we being the competitor think the miles per gallon is less. So our alternative hypothesis is what we see there at the bottom, that we think the mean miles per gallon is less than 29.